Hello, everyone, and welcome back to my virtual classroom. Today, we're going to be talking about addition and subtraction, and I'm going to introduce you to a concept known as cognitively guided instruction, or CGI. Not the CGI you're used to in movies these days, but a very old mathematical teaching idea related to how children think about addition, subtraction, and all of the operations. So the first thing that I want to do is talk about what makes problems difficult for children. So in just a moment, I'm going to put several pairs of problems up on the screen, and I want you to decide which one you think would be more difficult for a child, or if you think they are equally difficult. And I want you to think about why you're thinking that. So, what is the reasoning behind what makes a problem difficult, really, is what I'm getting at here. And one little hint I'll give you is you can think about whether or not it would be easy for a child to model the problem. So, we've talked about modeling. We had our models up on the slides in a prior presentation. So I want you to remember that and think about whether or not it's easy for a child to direct model. And then again, just thinking about what it is that you're considering when you're deciding how difficult a problem is. And the reason we want to be thinking about this is because as teachers, when we decide what types of problems to give our kids, we need to understand where this might be in terms of their progression. So are we giving them a really hard problem that we think is easy? Are we giving them a problem that builds on what we know they already know? So these are the kinds of things that we need to be thinking about. Okay, so here are the problems. I want you to pause here for a moment and again decide. So for every A and B pair, so there's four pairs, I want you to decide which one is more difficult, why you think that, and maybe consider about whether or not it's easy to model. So pause here and take a moment and do that for yourself. Okay, so don't forget your direct models are going to remind you that this idea of direct modeling actually determines how difficult a problem is, especially for our youngest learners who are just learning about operations. So as adults, we think about all these things that are listed here. So we're thinking about things like how long is the text? How complicated are the words that we're using? Is it a difficult operation? Because we have these preconceived notions of what the problem wants us to do automatically. Are the numbers big? Are the numbers small? Are they fractions? Things like that. So those are all the things that we consider. What children are going to be more focused on and what's going to determine difficulty for them are these things for sure. I'm not saying these are not important, but also how easy it is to directly model the problem. So if you have something that they can clearly follow the action of the story, and I'll get more into that in just a moment, that is going to make it easier for them to solve than something that's very difficult to model or more difficult to model. So that's not to say you shouldn't consider all of these things like text, number size, operation, all of that. It's to say that the direct model piece is very important for our youngest learners. So I want you to just look at this problem now. So I have here just a kind of a problem showing the relationship between 7, 8, and 15. And I want you to think about how you would think about this number fact as an adult. And for many of us, we would be thinking of 7 plus 8 equals 15, right? That's the way we think about it. That's what makes sense to me. But for children, that's the part whole that kind of underlies everything. But CGI says that kids are more flexible with their thinking. So, for example, these different models, numerical models, not direct models, um, actually illustrate this quite well. So students can be more flexible in terms of thinking, where is the missing piece? Whereas we kind of think about part, and whole, but they're just thinking about missing piece related to the what the problem is asking them to do. And so the great thing about this is that if we build on that flexibility, it can allow them to be more fluent with their number sense later on, which helps, of course, with all the other mathematical ideas they're going to encounter. So here, just as a summary, the kind of two important parts that we're going to be talking about in CGI are the problem action or structure. So meaning, is it easy to follow the action of the story? Are they joining? Are they separating? What information is given? And is that action easy to follow? So is it a story that tells me what to do? So Dr. Bonner has 3 pens and Tammy gives her 2 more. how many pens does she have now? That's easy to follow because they can model that out. Whereas if it's something like Dr. Bonner has 5 pens and Tammy has 3, how many more does Dr. Bonner have? They can definitely model that by laying them out, but there's not an action to it, if that makes sense. So the joining and separating is more action oriented, whereas those comparisons are a little more difficult to model. And then the location of the unknown value. So what number is missing? The 7, the 8, or the 15? So I'm going to go back here. So here in this one, the 8 is missing. And that's what I'm going to get more into this in just a minute too, but that's what we call the change value. Here the start value is missing, and here the result is missing. Okay, so we have three parts to these. And the interesting thing when you start thinking about this and going a little more in depth with CGI is that there are real benefits to having students be able to think in these different ways and giving them problems with different missing values. Because something like this one or this one, especially if you give them a problem with a missing middle number or missing start value, then what they can do is actually use kind of any operation they want to solve it. So you might have some kids who set it up as an addition problem like this, and you might have others who just use subtraction or they just know the fact. So lots of interesting opportunities there. So this is the CGI chart. I'm going to also drop this in your folder of things for today. And this just lays out really nicely the ideas behind CGI. So I talked about the two things that are most important are the action of the problem and the location of the unknown value. And this chart kind of goes from easiest up here, harder this way and harder that way. So when we have and these are the problem types right here. So a join problem would be something that generally looks like addition to us. Okay, so a student can usually solve like a separate problem. You can solve that multiple ways, but we call it a separate problem because of the wording that we see. So a join problem, if it has the result unknown, that means that final value is going to be unknown. The change is that middle value, and the start is that first value. So the easiest type of problem for a child to solve is going to be a join problem with the result unknown. That's like the easiest. So that would be the Dr. Bonner has 5 pens, Tammy gives her 3 more. How many does she have now? The result unknown. A join problem with a change unknown value. So Dr. Bonner has 5 pencils. Tammy gives her some more. Now she has 8. How many did Tammy give her? That's more difficult. And then a start unknown. Dr. Bonner has some pencils. Tammy gives her 3 more. Now she has 8. How many did she start with? Is even more difficult for them to model. So just thinking through, because the more information you have to just follow the story, the easier it is to model. And although we're given kind of the same amount of information in each of those examples, changing the unknown value makes it more difficult for children. Okay, and then on this side, the action of the problem. So a join is the easiest because you're just taking a group of things and then adding more to it. Separate is a little more difficult, although those are kind of interchangeable, join and separate. They're kind of the same level of difficulty, but separate can be a little bit harder to model. It doesn't come quite as naturally. And then grouping, which is really just our multiplication or division. So of course, like repeated addition or grouping. And then the idea of a part whole is very hard to, it doesn't have action. So this would be something like there are 5 green marbles and 3 blue marbles. How many are there altogether? So even though the students can again lay out 5 and 3 and then add them together, there's not an action of giving more or taking away or things like that. So it's more of a compare situation. And the compare problems are similar to that too. So just keep in mind that those are the 2 main factors when you're determining the difficulty of a problem, the location of the unknown value and whether or not the problem has action to it. Okay. So join and separate problems are generally the ones that have action, and then the other types have less of a followable action. The location of the unknown goes from on the left-hand side here, kind of like easiest to most difficult. Okay, so that's kind of the overview of the CGI chart. Okay, so interestingly, you might notice that we see in math textbooks, most often we're going to see the result unknown. So I pulled some examples here. We use the same examples each semester just because it's always interesting to look. So you can take a pause here and just look at these problems. And these are all examples of result unknown problems. So they're given the start value and the change value for these. These are subtraction problems or separate, but they all are missing the result. So the student can basically just make it a process, right? So they're no longer problem solving, they're just repeating, repeating, repeating. So if your goal is just practice, this might be a good one. But if your goal is building fluency, this is not an effective worksheet. Okay, and then same thing here. So this one we've got a mix of addition and subtraction, but we see that they're all result unknown. And so the students are learning a procedure that's not always going to be reliable when they don't have this exact information. So again, we're not teaching them to follow the action of the problem. We're not teaching them to follow the action of the problem. We're just teaching them to combine or separate, right? So we want them to think more fluently. So this is just to illustrate that oftentimes in textbooks, you're going to find these types of problems, but you really need to switch it up as a teacher. Okay. So I want you to just kind of pay attention to that as you're going through your curricular materials, maybe in your fieldwork classroom. And if you do have I have seen more recent curriculum that have a greater variety of problem types that are really focused on CGI, which is great. I also want to mention here that this structure of CGI is for you as a teacher, as a teacher tool. This is not for you to go to students and say, you need to categorize the problem. So you don't want them to know they're solving a join, result unknown problem. What you want them to do is experience a variety of problem types, but solve it however makes sense to them. So we're not trying to categorize problems for students. We're trying as a teacher to understand that so that we can then give lots of different experiences for students. Okay, so now I want to move into addition and subtraction strategies. So CGI is kind of laying the foundation, and now we're going to talk about what happens after that. So once students kind of move into strategies and more fluent numeracy, once they understand the operation itself. So this is a typical progression for addition and subtraction. So again, direct modeling, which we talk about with early number, is kind of the first step. So always remember, Tyra Banks and RuPaul start us off with that direct modeling. Then students generally move into counting on or counting down or back. So what this looks like is students are going to like if you have, again, the fact like 8 plus 5, they're going to start with 8 and then go 9, 10, 11, 12, 13. So something like that where they start with, and it could be either number. They don't have to start with the larger number, although that's the most efficient way, but either way will work. And they're able to just count on. So we're moving away from a model and into a counting strategy. Sometimes you'll see some overlap or combination of those. So they might use a model and then count on or count back. But either way, that's kind of the next step that you're looking for. So if you have a student who is struggling to count on or count back, this progression information is useful because you can say, okay, let's step back and model that problem until they're comfortable enough to start counting on and counting back. Often it happens pretty naturally because the direct model is effective in getting the correct answer, but it's inefficient, it takes a long time. So they'll kind of naturally move to counting on and counting back once they're comfortable with that and fluent. So most K through 3 students are going to use direct modeling and derived fact strategies. But a lot of times you'll see this counting on and counting down as an in-between step. And if you don't, you may want to encourage it. So derived facts are just what they sound like. So once a student counts on and counts back enough, they start learning those facts. So instead of going 8, 9, 10, 11, 12, 13, I just know 8 and 5 is 13. Or I might do something like 8 and 2 is 10 and 3 more is 13. So something like that where we're, again, combining counting on and counting back, but doing it in a more efficient way that leads to that just memorization of the fact. But if you're following this progression, then what you're going to see is that if they've had the experience with modeling, they've had the experience with counting on, counting back, the derived facts they will remember because they're based in a really solid conceptual understanding. If they just learn the facts without all of those experiences before, they're going to be hard to retain. Okay. So Then after that, you're going to get to recalled facts, which is where they just know the fact, and then algorithms, which we're going to talk about later in the semester when we talk about place value. All right, so thinking about this idea of moving beyond direct modeling into accounting strategy. So this is, again, moving from this direct model, which is what we see with our earliest learners, into this counting on and counting back. You want to think about kind of encouraging students to do this because it's more efficient. It's not necessarily to physically represent, it's just a strategy to get from one number to another. And they'll often use, again, their fingers or concrete models for counting, like I mentioned, and sometimes they can even hold a number in their head and count up or count back, which is great too. Okay, so here's an example. Sarah has $8. She wants to buy a game that costs $17. How many more dollars does she need? So we're looking for a change value here. So I want you to pause here and think about what this might look like. Actually, you could think about a couple of different things. You could think about what this might look like as a model. This one's a little more hard to model because we're finding a change value, but it's still possible to model because it's a join problem. And then I want you to think about what this might look like when a student uses a counting strategy. Okay, so this one, I kind of, I'll just go ahead and go here. But I want to make sure I'm showing you the problem while I'm saying this. So this one for a counting strategy, I would anticipate a student saying 8 in their head, maybe, or having 8 objects on the table. And then they're going to go 9, 10, 11, 12, 13, 14, 15, 16, 17. So I have 9 things. Okay, so I know my answer is going to be 9. So 8 and this number 9 are going to give me the 17. So that's kind of what a accounting strategy would look like. You may also have students who do some version of this, but the other way. So they know that they need to take the difference between 8 and 17. So 17 minus 8 is going to give them 9, which also gives them the correct answer. And that's the nice thing about CGI problems is that they can solve it in multiple ways. And all of those are great. And if you can get them to share those, that's even better because then they see different ways to solve it. Another good thing about this type of problem and the numbers that we picked, if you'll notice that 17 is close to doubles for 8. So students might use doubles. So they might use to learn certain combinations of numbers before others, especially doubles is a good one because oftentimes that just sticks with them. But if you are building fluency, then what they're going to be able to do is say, well, I know 8 and 8 is 16 and one more is 17, so 9 is the difference. And that's where you want to be. That shows great fluency. That's really close to a derived fact. So that's great. So doubles, combinations to 10 is another good one. Like I mentioned, when they kind of like use part of the add-in to make 10 and then use the rest later. And they'll use those things that they do know to derive new facts, which is great. So like when you see them creating even new strategies, I see my daughter doing this all the time and I always get really excited. But like if they know how to like, I don't know, I saw a student the other day doing something where they were supposed to multiply by 50, so they divided by 2 and multiplied by 100 or so, and the student was explaining it to me and I was like, that's super awesome because it like shows a real good understanding of what's happening with numbers, but is something I never would have thought of. So, but it works and they understood why it worked, and so it was a great strategy. Okay, here's another example. Kelly had some glitter pens and she got 6 more for her birthday. Now she has 11 glitter pens. How many did she have to start with? So take a moment here and let's think about what type of problem this is. So from my teacher perspective, I can tell this is not a result unknown, right? Which is great. So I know I'm going to have some more flexibility in thinking about how to solve it. And what I'm seeing is at the start value. So how many did she start with is the unknown. So take a moment, pause the video, and think about how a student might use a derived fact to, or actually any strategy, but especially a derived fact to solve this problem. Okay, so for this one, Kelly had some glitter pens, so we don't know the start value. She got 6 more for her birthday. Now she has 11. So again, with a derived fact, a student might say, well, I know that 6 doubles is close to 11. It's 12, but it's actually 1 less. So 11 is 1 less than 6 doubles, right? So then I know my answer is 1 less than 6, which is 5. They might also say, I know that 5 doubles is 10, And then 6 is going to give me one more, which will give me 11. So I know 5, 5, and 1, which is 5 and 6. They might also, if you had a student using accounting strategies just to kind of play this out, it'll be similar to the prior one where we thought about counting on, so counting from 6 to 11 or counting back from 11 to 6 and noting the difference. And if you had someone who needed to model, they might lay out 11 and take away 6, or they might lay out 6 and count up until they get to 11. And all of those are good strategies. So all this to say that elementary math is not elementary, which is a quote that I love because it always seems so simple, but really there's so much that you're laying the foundation for. So just something to keep in mind as you're moving forward in your field work. Okay, so that's, you see our friend the kitten here, so you know that's the end of the the end of the presentation. Just make sure that you are completing your readings each week or the other assignments that are listed in the syllabus. Make sure you're paying attention to assignments that are due as well, if you haven't already. And just keep in mind that you're brilliant and you're doing a great job, and I will look forward to seeing you next time.